Okay, so we're back at this point and we're going to try to finish off BJT terminal currents. Now, I know the last part of this lecture was pretty rough in terms of all the theoretical derivations, but hopefully now we can bring it down to something that is simple, which you can understand, and is honestly the most useful part of this lecture. And so if we do a little bit more algebra and trig, we can use what we had before and simplify it down to the following equations. And so I have an equation for my emitter current here, I have an equation for my collector current, and I have an equation for my base current as well. Okay? And so the first thing I want you to notice, and you see I highlight this here, is that all these equations share in common this delta PE term. And if you recall, delta PE was something delta P, for instance, was something we had calculated for diodes as the excess holes that show up on the N side of a PN junction, right? And so we're going to use that here as well. And it's important to remember that it is a function of voltage applied across the diode. And for this specific case of the BJT, delta PE was P sub N, the normal minority carrier concentration of holes in the N-type material, times this part, which looks pretty much like the diode equation, where the voltage is the voltage across the emitter base junction. Okay? Now, what this means essentially is that if I increase my forward bias across the emitter base, I expect to see more holes diffusing over into the base, right? And so I can see that my emitter current will go up exponentially with delta PE, increasing exponentially as well with voltage. So I increase my voltage, this goes up exponentially, and therefore my emitter current goes up exponentially, which makes sense because my emitter current goes up exponentially with forward bias across this diode, right? Look at collector current. Collector current also goes up exponentially. Collector current has delta PE in it as well, and that makes sense. If I have an exponential number of holes being injected into the base, and most of them make it to the collector, then I should see the same exponential increase in holes drifting out through the collector. So that makes sense. And then lastly, look at the base current too. The base current also goes up exponentially with delta PE, okay? And that makes sense as well. If I have all these extra holes coming across here, right, and the average hole concentration is increased, then there's going to be more recombination with electrons, right? And so I will need more base current to bring in electrons to recombine with the increase in holes moving across here. It should also make sense because we know that for a BJT, we know that our collector current is equal to the amplification factor, right, times the base current. Well, if these are proportional, right, and this is my proportionality factor, is the amplification factor, then if collector current goes up exponentially, of course my base current goes up exponentially as well. So this all should make sense. And again, when you calculate delta PE, if you look inside here, this P sub N here, down inside here, let me move this here, this P sub N down inside here is the minority carrier hole concentration in the N-type base, with no voltage applied, and then that becomes an excess or goes to zero for the case. Excess if you forward bias, and goes to zero if you reverse bias this. Okay? So key point, all the currents in a BJT increase the same as we increase the voltage across the emitter base diode, which again should make perfect sense. So at this point we're left with all this other stuff though. So what is all this other stuff? So let's start to try to understand. Okay, so the next term I want to look at is the blue highlighted term out front here. Okay? And so you should be looking at this and already you might be able to recognize this. So let's do this. Let's take this stuff in blue and I want you to steal the P sub N that's inside delta PE and group it with this. Okay, so let's do that. We'll steal, let me get my pen out here. We'll steal P sub N out of here and we'll group it with these terms here. Okay? Well, if we do that, you end up with the following. Okay? And you should recognize this. You've seen it before. So you remember when we had a diode, the reverse saturation current, I naught, was calculated from QA, right, charge of an electron, the area. There's Q and A up there as well. And then I had the contribution from the N side of the diode and the contribution from the P side of the diode, okay? And so what you're wondering at this point is, well, for a diode, why am I only dealing with the base side, P sub N? What happened to N sub P here? Well, let's think about this, okay? Let me see if I can erase this real quick. It doesn't want to erase. Okay. Well, so what happened to the P side here? Okay. Well, remember, this is a P plus N diode. So if it's P plus N, this is the N-type concentration on the P-type side. If P is heavily doped, N sub P is very small, and I can basically get rid of this term, right? I can get rid of this term. So that makes sense that we also look at this diode in terms of only the N side contribution to I naught, because P sub N is much greater than N sub P. And the other reason why this should make sense is the whole thing we did when we derived currents for the BJT is we derived them for diffusion a current equation in the base only. If we did all the derivations in the base, it kind of makes sense that it should be dependent on parameters in the base, right? And so at this point, this is getting simpler, okay? We've got this term and these terms out here, which I, again, steal the P sub N from delta PE, and it looks like I naught. The last thing I need then is some way to differentiate between these components, because if I look at these right now, these parts of the equations are all identical. And so something must be off because I know they're not identical. So that brings us to this final term out here. So what do these hyperbolic trigonometric functions do? Well, they are basically what differentiates between the magnitudes of the emitter current, the collector current, and the base current. I know with the BJT that if I have amplification, the emitter and collector currents are much greater than the base current, and that's exactly what these functions do. Essentially, they give you the ratios that lead to amplification factor. Okay? So, let's look at these terms, and here's the hyperbolic cotangent, which is equal to the 1 over the hyperbolic tangent, which can be also equated to this following equation using just exponentials as a function of x, okay? And so x in this equation is WB over LP, okay? So when I write these here, I just don't want to write all the WB and LPs. Substitute in for x, WB over LP in for x, and then you can calculate the same as hyperbolic cotangent of WB over LP. So let's look at how these things turn out. Let's assume that I have a BJT where my base width divided by my diffusion length, WB over LP, is 0.01. And that's a reasonable number, because if you think about it, if I want a BJT, I want a very narrow base width, so I want this term to be small, and I want the holes to get across without recombining in the base, so I want a long diffusion length for the holes. I want this to be large. If this is small and this is large, then their ratio should be small as well. So if you substitute this x in here for the emitter current, you'll find that this gives you about 100 for that. I can do the same thing for the collector current, substitute it in here. I get close to 100 as well, and that makes sense. If I have a really good BJT, the emitter and the collector currents are nearly equal, okay? Most of the holes in the emitter turn to holes that come out the collector. And lastly, if I substitute it in here, you'll find I get 0.01, which is much smaller. And so what that essentially tells you for this BJT, my amplification factor would be 10,000, right? The ratio between my base and collector current, which is just the hyperbolic trig functions here, if I look at these two, would be 10,000, 100 divided by 0.01, okay? So, again, remember we want WB smaller than LP for good design, so the holes get across without recombining. Typical ratios of WB over LP are 0.1 to about 0.001. That's the range we'll typically see. And you can remember, one simple way to remember this is if I have e to the 0.01, that's equal to 1.01. And here's some examples from the book. If I have a base with 10 to the 15th, LP is 108 microns. base width is 1 micron. I substitute these in just in the hyperbolic trig function portions, and I can calculate my amplification factor to be 832. Notice that to get amplification factor, all I need is to get the ratio of these terms, and so I could do it just with these values here and get my amplification factor for the BJT. This is exciting now because now I have a way to basically predict amplification for a factor for a BJT using a geometry, the base width, and diffusion length, which I can calculate from doping level, and I can then get amplification factor. So let's bring it all together and review it one last time, okay? And you should be absolutely solid on what each of these things basically represents. The blue stuff out front is basically reverse saturation current for a diode. And remember, the BJT is all basically diodes, forward or reverse bias, so that makes sense. And again, remember, to make this reverse saturation current, you have to basically go into P sub E, delta P sub E here, steal the P sub N, and group it with these terms here. The yellow stuff here is the effect of emitter base voltage, and that means that all the currents in the BJT either go up together or they decrease together, which makes sense if you think about how it operates. And the last thing I need is a way to differentiate between these things, because if I have a good BJT, I know they're not equal, and so you have these hyperbolic trig functions, which essentially make the emitter and the collector current much greater than the base current. And lo and behold, you know, the exact type of things we said that were important for a BJT, we said we cared about base width was important, right? And we said that we cared about having a low doping level in the base. And if we have a low doping level, that leads to a large diffusion length in the base. And so basically you see this equation tells us exactly what we wanted for the BJT. If you want good amplification with the BJT, you want a small base width and a low doping level, and the doping level appears in here in terms of the diffusion length, which is a function of doping level. Okay, I'm going to show you one way real quick to do a simpler formula for the base current. So if my base current, I can get rid of the hyperbolic trig functions as follows, and you'll see why. So if I have a good design, meaning I've got a small WB over LP, it's a small number, then you can show via series expansion that base current can be calculated as follows, okay? Where I've got charge, area, width of the base, delta PE, 2 divided by tau P. So what does this equation say? Well, this is really simple, okay? Look at my plot of charge across the base. Remember, if I assume that I have an excess at one end, delta PE, of holes diffusing over from the emitter into the base, and at the other end I've got 0, if I were to connect them with a straight line, and I know it's not actually a straight line, it's a little curve, but just assume it is, you'll notice that the total charge under this is basically the area of a triangle, right? And so the area of this triangle would be 1/2 base times height times charge. There's charge, 1/2, base is WB, height is delta PE, and the last thing I need is the area as well, okay? And so I get my total charge out of that, and that makes sense too because the units for delta PE are 1 over cubic centimeter, and then if I have area times width, that's cubic centimeter, all my centimeters cancel out, and I'm left with just charge in the front. And so if I put this, and I look in here, here's my 1/2, and the rest of it, here's 1/2. This is the same as this. And all this equation is saying here, if you look at this then, is IB is QP over tau P. That should make complete sense. If I on average have a number of holes, or a number of holes, QP, so that's my number of holes I have at any given time diffusing across the base, and they are recombining with a lifetime of tau P, that gives me coulombs per second, which is current, and that gives me my base current. So that's another way I can calculate base current, which should make complete sense to you as well. Okay, so a little bit more on how we can design the BJT optimally. So to simplify our calculations, we assumed our emitter injection emitter injection efficiency was 1, which is a fairly safe assumption. However, if you're a BJT designer, you would like to know in practice that it's, that it's actually not unity, and you'd like to know how to calculate it, or how to design the BJT to get it as close to unity as possible. So in practice, it's not unity, and so what can you do to design it to be as close as possible? Well, remember, gamma, or emitter injection efficiency, can be calculated from these current components, and we just had hyperbolic trig functions basically for these as well. And so if we put those in there, you can solve, and I'm not going to do the math, you can solve for emitter injection efficiency to be calculated as this, which can be approximated as follows. Okay, it's actually not too bad. So if you look at, well, what's this term here? L sub, well, in this case, you don't need all these terms, but for example, in here, L sub n sub p is whole diffusion length in the n-type base. Okay, so L sub p sub n would be electron diffusion length in the p-type emitter. And you can see, for example, there's electron mobility in the p-type mobility, in the p-type emitter as well. So now you can put semiconductor parameters, which are easily calculated for various regions of the BJT, and put them inside this and calculate emitter injection efficiency. It's also good to understand base transport factor, how much of your emitter current turns into collector current. We want this to be close as 1 as possible. That's easy to calculate because that was the ratio of IC over IE. We had those hyperbolic trig functions. All this stuff cancels out, and you're left with just 2 hyperbolic trig functions, which gives you this hyperbolic secant of WB over LP. That gives you your base transport factor. Last topic. So that wraps up terminal currents for BJTs. The last topic I want to touch on is a heterojunction BJT. Actually, yeah, heterojunction BJT, or HBTs. Okay? And what they use is a wider band gap material for the emitter. So why do you use a wider band gap material for the emitter? Well, here's a conventional BJT. And we said if we have really good design, we'd like to basically inject electrons here. They stay here, and the only time they disappear is when they recombine with holes in the valence band. But we know that in reality, some of the electrons are going to go this way. They're still going to diffuse this way. Even if this is lightly doped, I still have some electrons diffusing this way. So what could I do to basically block the electrons from diffusing this way? With a heterojunction bipolar transistor, a heterojunction meaning I have 2 different types of semiconductors, no longer just like silicon and silicon, what I can do is I can have the emitter be made from a wider band gap semiconductor that lines up as follows. And so with this wider band gap, so it has a wider band gap than the material here, you can see that my conduction band has been pushed up. Now I've got a much larger barrier for diffusion of electrons here, and so if I inject electrons, they just stay here until they recombine with holes, and I've eliminated this portion of base current, which is going to give me a smaller base current and a higher amplification factor. If you want to, and of course this gives me a better emitter injection efficiency. Again, emitter injection efficiency, I want all holes and no electrons, so of course it improves my emitter injection efficiency. If you want to calculate how much this helps you, it's actually pretty easy and it makes sense. And so we've already shown, and you did this in our homework in the past lecture, we've shown in the previous lecture as well, that my hole current divided by my electron current is just the ratio of the dope, is proportional to the ratio of the dopants, right? Well, in addition to that, I can see it be exponentially dependent on this delta EG here, okay? And so my delta EG is right here. That's my delta EG that increases the conduction band. And the reason why it's exponential is because it's all related to electrons trying to diffuse over here, and as you basically go create a bigger barrier, just like a diode turning on, essentially a bigger barrier, you'll be able to tap into less and less of that exponential distribution of electrons because of the Fermi distribution. So it does have an exponential relationship in that if you increase delta EG, my electron current goes down exponentially compared to my hole current. And so this can have a big effect at blocking the electrons there. Typically use materials such as, for example, aluminum gallium arsenide on this side and gallium arsenide on this side, which is narrower band gap. Again, this side would be the aluminum gallium arsenide because the aluminum increases the band gap energy. Okay, so let's finish up and we'll review. So to get the current equations, we solve for what in the base? Drift current equation, diffusion current equation, neither or both. You should be able to answer that. For our equations we have here, basically what's the yellow? Okay? And you should be able to say, well, how does that affect currents as voltage changes? Does it change them all equally or does it change them differently? Next question, is it good that our currents respond linear to base current? Okay? And so if base current goes up, these go up proportional with that, meaning they go up linear. Well, here's your two choices here. You could either say, not that I can think of now, or you could say the right answer, which is, wow, I now have a single semiconductor device that linearly amplifies current. That's pretty cool. And it's pretty amazing that this device works that well. Okay, so for our equations, what's the blue out here in front? That's the next question. And the hint, and you should be able to recall this, is that the BJT is made of just diodes, and this is just a key part of the diode equation. So remember which part that is. For our equations, what's the pink out here at this end? Well, the question really is how does it affect our currents? And the hint is I need these. Without these, would I still have an amplifier? If I didn't have this, would I have amplification? Last question. If we made WB really large, what would our circuit equations reduce to? If I made WB really large, what do you think is going to happen to these? You could either do the math, but to make this easier, just trust your instincts. If WB becomes really large, you basically get two separate diodes. Let me draw that real quick. If I make WB really large, you basically get something that looks like this. And so there's my base, there's my emitter, and there's my collector. If you look at this from a circuit standpoint, you should be able to figure out that this is not a BJT and this is not a current amplifier. In fact, it's a circuit that really doesn't do much of anything for you. Last question is, why do we make HBTs? It improves our emitter injection efficiency, but then again, how does it do that? So that's the end of this lecture. I've got a couple more slides I'm going to show you, but those are optional. They just show you how you might make a BJT, but they're not mandatory to be reviewed. But some of you might find them interesting. Okay, so if time allows, you can go through this example of how you make a heterojunction bipolar transistor. So this is from a master's thesis by a group at Israel Institute of Technology. Okay? And they're making an indium phosphide-based optoelectronic integrated circuit for optical communication systems. So this is basically a BJT, which a photon of light comes in, and it detects it kind of like a photodetector, but it also has amplification. When we get to optoelectronics, I'll tell you how it works. But let's just look at how you make this type of a BJT. So the first thing you do is you start with the wafer, and you grow up all these layers of material on it one by one. And the last thing you'll do is you'll pattern an emitter metal contact. So this is my emitter metal contact on top. The next thing you'll do is you'll use some kind of chemical that comes down and etches away all the material here, but it doesn't etch the metal. And so as this is coming down and etching, this protects the materials underneath it, and now I've got an emitter contact, and here's my emitter right here. And it etched away all these other materials. We'll keep moving forward. The next thing I do is I'm going to put down on top of this is my base metal contact. That makes sense. Look at this thin layer. Remember my base is thin? This layer right here is my base. Okay? Okay, the next thing I'm going to do is I'm going to passivate the metal contacts for the emitter and the base with a polyimide polymer. This is a polymer which is highly protective of these, and it's protective enough then I can then use this protective layer and then etch down and use a chemical to remove the other layers away as well, but keep this here. That reveals my collector. Here's my collector here. Next thing I'm going to do then is I'm going to put a metal contact here on below my collector. This is my subcollector, hence it's called a subcollector. All the subcollector does is allow current to flow from the metal contact underneath here to the collector. And so if I looked at my current flow for this device, it goes from the emitter through the base out through the collector like this, okay? And I can modulate the amount of current moving in this direction by putting current or voltage on the base metal electrodes. The last thing you'll do when you're almost done at this point is that you're going to etch down outside the sub-collector too. The reason when you want to do this is maybe I have a BJT here, maybe I have another one over here and another one here. This way you electrically isolate the BJTs from each other so they don't interfere with each other. I'm then going to take that polyimide polymer, I'm going to cover the whole thing and coat it with that, and I'm going to bring a metal contact here which is going to make contact all the way up here onto my emitter on the top. You'll see this on the next slide here. And so here's the process steps. You're moving through it and you're basically building everything up layer by layer. You can follow through you can see the captions here. They'll tell you exactly what they're doing for those. And when everything's said and done, the next thing you do is you put your BJT down on this probe station. You, under a microscope, bring some wires to make contacts to it. You hook it up to some kind of network or some kind of high-speed measurement system that'll let you measure the response. They have a simple circuit model, and you can see here's the collector current versus VCE. If you look in here and you look at the step size they talk about for the currents, you can see that the amplification factor is about 75. Okay, and this is a great lead-in next. In this this thesis for this master's student, they're showing this simple circuit model. Well, that's what we're going to talk about next time. So I'll tell you how do you make a simple circuit model for a BJT, which is really helpful when you want to put this in a network type circuit in electronics, because I don't want to put all those hyperbolic trig functions, right? Wouldn't it be great if I didn't need all those hyperbolic trig functions, etc., and I could represent things in terms of just simple current sources and resistors and things like that? And so that's it, and I'll see you in class.